National Electrical Code Section 230.98 states that service entrance conductors cannot be tapped on the load side of a service disconnect or overcurrent device. National Electrical Code Section 250.24 states that service entrance ground conductors must be installed on the supply side of the service disconnecting means. National Electrical Code Section 310.15b7 states that conductors tapped from the load side of a service overcurrent device must be provided with proper overcurrent protection. Tapping on the load side of a current transformer, or CT, service may result in inaccurate metering, as the CT will only measure the current flowing through the conductors on the supply side of the tap. Using the conductors on the load side of the CT service may not provide adequate protection against fault currents. To comply with code and safety requirements, it is recommended to extend the service conductors. Extend the 500 Ohm service conductors from the CT cabinet into the building. Install a subpole inside the building and connect it to the extended service conductors. Provide overcurrent protection. Install 20 amp circuit breakers in the subpanel for the two 20 amp circuits. Ensure proper grounding. Install a grounding electrode system at the building and connect the subpanel ground bar to it. If it is not feasible to extend the service conductors, an alternative solution could be to install a fuse disconnect with a CT window at the CT cabinet. This would allow for current monitoring and provide overcurrent protection for the tapped conductors. However, this solution may still result in inaccurate metering. When dealing with electrical systems, understanding and adhering to the National Electrical Code, or NEC, is paramount for safety and compliance. One common question arises regarding tapping into the load side of a CT service. Let's delve into the code concerns, technical issues, and recommended solutions. The NEC has specific stipulations regarding service entrance conductors. Section 230.98 explicitly states that these conductors cannot be tapped on the load side of a service disconnect or overcurrent device. This rule is in place to ensure the integrity of the service and to prevent potential hazards. Similarly, Section 250.24 mandates that service entrance ground conductors must be installed on the supply side of the service disconnecting means. This ensures a proper grounding path for safety. Furthermore, Section 310.15b7 addresses conductors tapped from the load side of a service overcurrent device, requiring them to have proper overcurrent protection. These code requirements are not arbitrary, they are designed to safeguard the electrical system and prevent potential dangers. Beyond code compliance, there are technical concerns to consider when tapping into the load side of a CT service. One significant issue is inaccurate metering. A CT is designed to measure the current flowing through the conductors on its supply side. If a tap is made on the load side, the CT will only measure the current upstream of the tap, leading to inaccurate readings. This can have financial implications for both the utility and the consumer. Additionally, fusing the conductors on the load side of the CT service may not provide adequate protection against fault currents. The CT is designed to protect the entire service, and tapping into the load side can compromise this protection. In light of these code and technical concerns, it's essential to implement solutions that ensure compliance and safety. One recommended approach is to extend the service conductors. This involves running the 500 Ohm service conductors from the CT cabinet directly into the building. By doing so, you avoid tapping into the load side of the CT service altogether. Once the service conductors are inside the building, the next step is to install the subpanel. This subpanel will serve as the distribution point for the building's electrical circuits. It should be connected directly to the extended service conductors. Within the subpanel, you'll need to provide overcurrent protection for each circuit. This is typically achieved by installing circuit breakers. For the specific scenario of two 20 amp circuits, you would install two 20 amp circuit breakers in the subpanel. Proper grounding is also crucial for safety. You'll need to install a grounding electrode system at the building and connect the subpole ground bar to it. This ensures a low impedance path for fault currents, minimizing the risk of electric shock. In situations where extending the service conductors is not feasible, an alternative solution is to install a fuse disconnect with a CT window at the CT cabinet. This allows for current monitoring and provides overcurrent protection for the tapped conductors. However, it's important to note that this solution may still result in inaccurate metering. Electrical work should always be performed by qualified professionals who are familiar with the NEC and local codes. It's also essential to obtain the necessary permits and inspections to ensure compliance with regulations. In addition to the aforementioned points, it's crucial to consider the specific application when designing and installing electrical systems. For instance, the type of load being served, the distance between the service and the load, and the environmental conditions can all influence the design. Furthermore, it's essential to use appropriately sized conductors for the intended load. The NEC provides tables and guidelines for determining the correct conductor size based on ampacity, voltage drop, and other factors. Overloading conductors can lead to overheating, insulation damage, and even fires. Regular maintenance and inspection of electrical systems are also crucial for ensuring safety and reliability. This includes checking for loose connections, damaged wiring, and corroded components. Any issues should be addressed promptly to prevent potential hazards. When working with electrical systems, always prioritize safety. De-energize circuits before working on them, use appropriate personal protective equipment, and follow lockout/tagout procedures to prevent accidental energization. Electricity can be dangerous, and it's essential to take precautions to avoid injury or death. In summary, tapping into the load side of a CT service can raise significant code and technical concerns. It's crucial to understand the NEC requirements, metering implications, and overcurrent protection considerations. By implementing the recommended solutions, such as extending the service conductors, installing a subpole, and providing proper grounding, you can ensure a safe and compliant electrical installation. Always consult with qualified professionals and adhere to local codes to protect yourself and others from potential hazards. Furthermore, the selection of appropriate overcurrent protection devices is critical for ensuring the safety and reliability of electrical systems. Circuit breakers and fuses are designed to interrupt the flow of current when it exceeds a predetermined level, protecting equipment and personnel from damage or injury. When selecting overcurrent protection devices, it's essential to consider the ampacity of the circuit, the interrupting rating of the device, and the coordination with other protective devices in the system. The ampacity of the circuit refers to the maximum amount of current that the circuit can safely carry. The overcurrent protection device should be sized to protect the conductors from overheating and potential damage. The interrupting rating of the device refers to the maximum amount of fault current that the device can safely interrupt. It's essential to select a device with an interrupting rating that is greater than the available fault current at the point of installation. Coordination with other protective devices in the system is also crucial for ensuring selective tripping. Selective tripping refers to the ability of the overcurrent protection devices closest to the fault to trip first, minimizing the extent of the outage. This can be achieved by using devices with different time current characteristics or by implementing some selective interlocking schemes. In addition to overcurrent protection, surge protection is also essential for protecting sensitive electronic equipment from voltage transients. Surges can be caused by lightning strikes, switching operations, or other disturbances in the electrical system. Surge protective devices, or SPDs, are designed to divert these surges to ground, protecting the equipment from damage. SPD should be installed at the service entrance and at any sensitive equipment locations. They should be selected based on the voltage rating of the system, the expected surge current, and the level of protection required. Regular testing and maintenance of SPD are also essential for ensuring their effectiveness. Proper grounding is another critical aspect of electrical safety. Grounding provides a low impedance path for fault currents to return to the source, minimizing the risk of electric shock. Grounding also helps to stabilize the voltage on the electrical system and reduce noise. The grounding system should be designed and installed in accordance with the NEC and local codes. It should include a grounding electrode system, a grounding conductor, and equipment grounding conductors. The grounding electrode system should consist of one or more electrodes, such as ground rods, ground plates, or metal water pipes that are buried in the earth. The grounding conductor should connect the grounding electrode system to the service equipment. The equipment grounding conductor should connect the non-current carrying metal parts of electrical equipment to the grounding system. Regular inspection and testing of the grounding system are also essential for ensuring its effectiveness. Furthermore, it's important to consider the impact of harmonics on electrical systems. Harmonics are non-sinusoidal currents and voltages that can be generated by nonlinear loads such as electronic equipment and adjustable speed drives. Harmonics can cause a variety of problems, including overheating of transformers and conductors, nuisance tripping of circuit breakers, and interference with sensitive electronic equipment. To mitigate the effects of harmonics, it's essential to use harmonic filters or other mitigation techniques. Harmonic filters are designed to reduce the amplitude of harmonic currents and voltages, improving the power quality of the electrical system. They can be installed at the source of the harmonics or at the point of common coupling. In addition to harmonic filters, other mitigation techniques include using harmonic reducing transformers, oversizing transformers and conductors, and implementing power factor correction. Power factor correction can also help to reduce harmonic currents by improving the efficiency of the electrical system. Regular monitoring and analysis of harmonic levels are also essential for identifying and addressing harmonic problems. The electrical systems are complex and dynamic, and it's essential to stay up to date with the latest codes, standards, and technologies. Continuous education and training are crucial for electrical professionals to ensure that they have the knowledge and skills necessary to design, install, and maintain safe and reliable electrical systems. This includes attending industry conferences, taking continuing education courses, and reading industry publications. Furthermore, it's important to foster a culture of safety in the workplace. This includes providing employees with the necessary training, equipment, and resources to perform their jobs safely. It also includes encouraging employees to report safety concerns and to actively participate in safety programs. By prioritizing safety, electrical professionals can help to prevent accidents and injuries, protecting themselves and others from potential harm. In addition to the technical aspects of electrical systems, it's also important to consider the economic and environmental impacts of electrical installations. Energy efficiency is a key consideration in modern electrical design. By using energy-efficient equipment, such as LED lighting and high-efficiency motors, it's possible to reduce energy consumption and lower operating costs. Energy-efficient design also helps to reduce greenhouse gas emissions, contributing to a more sustainable environment. Furthermore, it's important to properly dispose of electrical waste, such as used batteries and fluorescent lamps. These materials can contain hazardous substances that can pollute the environment if not disposed of properly. Recycling programs and proper disposal facilities are essential for managing electrical waste responsibly. In conclusion, electrical systems are essential for modern life, and it's crucial to design, install, and maintain them safely and reliably. By understanding the NEC and local codes, implementing proper overcurrent protection and grounding, mitigating harmonics, and prioritizing safety, electrical professionals can help to ensure that electrical systems are safe, efficient, and sustainable. Continuous education, a culture of safety, and responsible environmental practices are all essential for protecting people, property, and the planet.